So in the previous session, we were looking at the quadrature sampling of the bandpass signal. So bandpass signal will be represented in the form of quadrature components, namely Qi and Gi and Gq. Right? We try to sample them separately after making them uh, after bringing them into the low pass versions of the same. Right? Then we send them using this kind of sampling procedure. All right. Once it is done, then we can even show that yes, this is a valid sampling technique because you can do the reconstruction. Right? So that's all about the quadrature sampling of the bandpass signals. We'll move on to the next topic. So here we are going to look at the concept of which explains what are the various effects of aliasing. All right. Effects of aliasing. Now, initially we saw that whenever you want to convert a continuous signal into the discrete, right, you need to perform the sampling, first thing. So once that sampling is over, we saw that, okay, what are the various versions of sampling you can perform, right, with the various rates. By changing the rates of sampling, what are the options we have, right? We checked that. And then we know that if the sampling rate, right, that is fs is much greater than twice the uh, bandwidth of the signal for a low pass signal, definitely yes, it's going to work fine, or at least 2W is required. Lesser than that will cause aliasing, right? Okay, now we know that, okay, if you follow the rules, right, no problem, right? So there will be what you call no aliasing and no problem with the sample. Okay. Okay. Now the other thing is that what if due to some reasons people could not follow the sampling, the rule of sampling. So that means, right? So that means, will there be any measurement for the effects, right? That right caused by this error, right? So will there be any measurement? Is it possible to measure how much error, right, we have because of the aliasing? Right? So that's what is the concept called as effects of aliasing. We'll try to measure, quantize, or we try to put a bound on the error that is caused because of the aliasing. All right. So our objective here is to put bounds on the error caused due to the aliasing. So this is our objective. So let us say, we'll once again, there is a small derivation over here. So let's start with the concept where we have a arbitrary signal g of t. Okay. So to put this bounds on aliasing, let's start with the a function g of t, right? So let g of t be an arbitrary signal. Let's use the Dirac-Coombe to sample that. Okay, so arbitrary signal sampled by using the Dirac-Coombe. All right, now How do you represent the sampled signals? So samples of g of t means every t gets replaced by n times ts, correct? So uh, you can write a ts sorry, you can write a ts over there, or even you can replace it in terms of fs, right? So let's try to continue. Let g of n ts represents the samples. The samples of g of t. Right. Now, let us assume that we followed the procedure to reconstruct the signal. Right? How do you reconstruct? Right? You pass it through a reconstruction filter. It will convert the g of nts back into the g of t. But now, let us say we have not followed the conditions required to eliminate the aliasing, right? Because of which there is aliasing. So, when I try to reconstruct the g of nts, it's very clear that I'm not going to get a g of t. So I will get a different version of g of t. Let's try to denote that as gi of t. Okay. So and so this is gi of t be the signal reconstructed. Signal reconstructed from the samples, right? So what are the samples? You can write g delta of t. What is g delta of t? This is the other notation for g of nts. So we know that we can write the g of nts like this, correct? So also when I say I'm writing about the g of nts, that's also equal to g of n by fs. So ts is equal to 1 by fs. So that actually means I can write g of n ts is also equal to g of n divided by fs. Okay, so don't get confused if you see g of n by fs in some other textbooks. Okay, fine. So normally, how do you get this back? You have a g of nts. I can convert that into g of g delta of t by using the formula that is called as the interpolation formula. Right? If you remember, we had derived the interpolation formula in the previous section. Right? So you can see that this is what we call as the interpolation formula. Right? So you can see g of n ts, you have 1 by 2w over there. So you apply this particular formula to get the g of t which is present on the left hand side. Okay, so let's assume that we have done that and we get this, and the signal we obtain is gi of t, right? So let's apply the reconstruction formula once again. This implies the gi of t is equal to, right? I'm using the same interpolation formula, right? That is summation n is equal to minus infinity n equal to minus infinity to plus infinity. Take the sample signal, that is g of nts, into the sinc function, correct? So it's a sinc of fs, sampling time, sampling frequency, times t minus n, right? So in the original derivation, we had fs is 1 by 2w, okay? But that 1 by 2w, you can try to replace, sorry, fs equal to 2w, but that was present over there. Now we try to replace it, okay, like this. So when that means, let me try to modify this. As I know now, I can try to replace, but the ts is equal to 1 over fs. So this implies, now I can try to rewrite that is equal to the same summation n is equal to minus infinity to plus infinity. I can try to write this as g of n divided by fs. okay, into the sink of Fs T minus N. Now, so this is what is the reconstructed, right? This is the reconstructed signal from the G of N by Fs. Fine. Now, how do you quantize or how do you decide that there is an error, right? How do you consider, how do you decide or how do you declare that yes, there is an error between this Gi of t and the G of t which was originally used for sampling? If you want to decide an error, right, it's the same thing, right? Whatever is the expected value minus this value, right? Expected value is G of t, right? And right, I subtract to get the Gi of t. I subtract the Gi of t from that. I get an error, right? So you see, that means I can now write, therefore, the aliasing error can be defined as, let's try to define that as a epsilon. Epsilon is equal to magnitude of the G of t minus Gi of t. So G of t is the expected signal, and I'm subtracting the Gi of t from that, which is the reconstructed signal that contains aliased version. All right, so let's try to call this as equation number 1. Okay, fine. Now let us try to right. Okay, let's try to do this. That is, I'll try to calculate the definition of the I'll use the definition of the Fourier representation get the G of t, right? So, but let's write the equation of G of t. What is the equation of G of t? It is, by the definition, minus infinity to plus infinity, use a G of f into e to the power j 2 pi ft df, right? This is the inverse Fourier transform equation. I have G of f, which is the frequency domain representation. You want to come back to the time domain means you should apply the inverse, right? So this is the inverse of Fourier transform. But now we know that, we'll quickly move back to the equation. We'll quickly consider, look at the diagram of G of f once. So if you want to come back to the G of, use the G of f to come back, right? I can try to write this as, sorry. Yeah, let's me assume this is the G delta of f, right? From which I want to come back, right? So what I can try to do here, right? You take this once and take its inverse. Take this separately once, its inverse, it's once again, like that. You see the G of f can be written as the, it says it's a summation, sum of different triangles, correct? There are so many triangles. How many triangles are there? N is equal to minus infinity to plus infinity. So many triangles are there, correct? So that means, instead of writing the inverse equation which we have used just now, right, I can also try to write it in a different way, right? So this means this is also equal to, now you see, I'll try to bring a summation into picture. So there is a summation, that is m equal to minus infinity to plus infinity. You actually have a G of f, okay, but the G of f exists only in a specific location. The location is actually identified by this one. You see, when I try to put m equal to say plus 1, or put m equal to 0, okay, when I say m equal to 0, right, I have to have the position from minus of minus 1 by 2 fs to plus 1 by 2 fs, correct? Because fs is what? Fs is equal to 2w, correct? So half fs means it is right by 2. It's w, and the lower limit becomes minus of half into 2w. So you see it is minus w2 plus w, isn't it? The limit where you consider this g of f is minus w2 plus w, correct? So how do I write that? I try to write that in terms of fs, because you see my equation has fs now. So that's why I'm not writing w over there. I'm trying to write in terms of fs. This is when m equal to 0, but I need to write for all the possible values of m. So just check whether this is going to work. I'll write the lower limit as m minus half times fs, and the upper limit as m plus half times fs. So check this for m equal to 0. What happens when you put m equal to 0? Lower limit is minus fs by 2, upper limit is plus fs by 2. Just now we calculated that, we understood. Okay. Moving ahead, when you put m equal to 1, what happens? When m is equal to 1, so lower limit is half fs, that is right, just w to 3w. Right? So that's what is required, correct? So like that, you can even check for minus 1, minus 2, plus 2, etc. All the values will be satisfied. So that's how I try to split this single integration into a summation and integration, where the summation takes care of which triangle you are trying to consider. So whenever you put m equal to 0, you consider this triangle. M equal to 1, this. M equal to minus 1, this. M equal to 2, and so on. Right? I will be able to move to the right and the left as required. So once again, since the m is being iterated all the way from minus infinity to plus infinity, it's going to do the same job like my complete integral, which is minus infinity to plus infinity. This is equal to, right? So I try to replace that, sorry, yeah, with the two integrals, like, sorry, one summation and one integral like this. I hope this is clear. Do you have any doubt here? Okay, so rest of the things remain same. So g of f into e to the power plus j 2 pi f t df. Right. Now, let us try to use one very fundamental formula. It's called as a Poisson's formula, and we have used this in signals and systems. Okay. So let me hold on to this equation, and I'll bring the Poisson's equation now, and we'll try to use that here. So let me give a number to this. I think we called that as 1. So this is equation number 2. Okay, so but Poisson's equation states that if at all you find a summation from, say, m is equal to minus infinity to plus infinity, a shifted version of a function, that is g of f minus m times fs, right? This can be simply replaced by 1 over fs. 1 over fs is a summation, that is n is equal to minus infinity to plus infinity. This will be g of n by fs into e to the power minus j 2 pi into nf divided by fs. So, right, the f by fs is in the denominator of that exponential. So call this is equation number 3. Right. So now what I try to do, right, in this equation, for the Poisson's equation, both sides I will multiply by e to the power j 2 pi ft. Okay, and I will also try to do the integration from minus fs to plus fs. So let me write what I'm trying to do now. Right, multiply both sides by e to the power plus j 2 pi ft. That's the first thing you're going to do. And right, integrating with with respect to f on the frequency domain from minus of fs by 2 to plus fs by 2. Oh, sorry, plus fs but divided by 2. So this is my limit. So let's try to write that now. So this, when you do, the equation 3 becomes like this. So that is integral minus fs minus of fs by 2 to plus of fs by 2. Fs by 2 is, I have a summation as it is. So summation m equal to minus infinity to plus infinity capital G of f minus m times fs, multiply this with e to the power j 2 pi ft, because you multiply by this, and integrate with respect to f. Okay, so integration with respect to f is denoted by df, correct? Df should be equal to, on the right hand side I already have a 1 by fs present. Integration, this is minus of fs by 2 to plus fs by 2, summation as it is. This is n equal to minus infinity to plus infinity, small letter g of n by fs. So there is already existing term, that is e to the power minus j 2 pi nf divided by fs. Then I am multiplying by another exponential, that is e to the power j 2 pi ft df. All right, now I'm trying to uh, do pure mathematical steps, right? I'll try to perform the change of the order of integration and summation. So that is pretty much valid. Okay, so that means, so this is what is going to happen. So I'll try to bring the summation outside. So this implies summation, I have m equal to minus infinity to plus infinity integration minus of fs by 2 to plus fs by 2, the g of f minus m times fs e to the power j 2 pi ft df is equal to, well, write 1 by fs outside, then I'll bring the summation. Okay, summation, this is n equal to minus infinity to plus infinity, have the function g of n by fs. So see, the integration happens with respect to f, so only the terms containing f will be used for integration. So that's why I'm bringing all the terms out. Now I'll write the integration, because this means only for the terms containing f. Okay, so limit minus fs by 2 to plus fs by 2. Okay, let me try to write like this. I'll club the terms. Okay, so I'll try to write a f here, because f is the one which we are integrating. Other terms you write as it is. So I have j 2 pi t minus j 2 pi n f by fs. F is moved out, f has been moved out, so it's fs. Okay, df. So that's the term I'm going to integrate now. So left hand side still remains same, so that is equal to 1 divided by fs. I'll still write the summation as it is, that is equal to n is equal to minus infinity to plus infinity. This is g of n by fs. So e to the power anything you integrate, it remains same, isn't it? So that is, now this is the result of integration. So I'll write inside a bracket. So e to the power f into j 2 pi t minus j 2 pi n by fs all divided by, it's whatever is inside the bracket. So that is j 2 pi t minus j 2 pi n divided by fs. Fine. So what is the limit? Minus of fs by 2 to plus fs by 2. You will substitute these limits for f. Right. So let's proceed further. So that means this is equal to 1 divided by fs summation n equal to minus infinity to plus infinity. This is g of n by fs into, so first term, when you put fs by 2, so this becomes e to the power fs by 2 times j 2 pi t. So this is e to the power j 2 pi t. So this is equal to, I'm trying to write the g of n by fs normally. Then let us try to substitute. That is e to the power, first term is fs divided by 2 times j 2 pi t minus j 2 pi n by fs. Okay, this is minus e to the power minus of fs by 2, same term. Okay, e to the power minus of fs by 2 into j 2 pi t minus, this is j 2 pi n by fs all divided by, this is j 2 pi t minus j 2 pi n by fs. Is it okay? Fine. So in the next step, let us try to simplify further. So I can see that e to the power something j theta minus e to the power minus j theta, right? I need a 2j in the denominator, correct? I can see that the j2 in the denominator as well. So let's try to write it in the required format so that I can write it in the, I can bring a sinusoid over there. Okay, so this is equal to 1 divided by fs summation n equal to minus infinity to plus infinity. This is g of n over fs, right? So how do I write this? So let me take a j2 pi, which is common, correct? And I'll multiply the fs into that, right? So that I'll bring this into some standard format. Okay, so when I multiply, what happens to the first term? So the denominator 2 will get cancelled with every 2 present over there, right? I can bring out the j pi, correct? So e to the power, I'll try to bring a j pi outside. Okay, fs goes inside, so j is not there, 2 is cancelled, pi is not there. So it is, right, fs into t, correct, minus, in the second term what happens, j is not there, 2 is not there, pi is not there, there is only n, right? Fs already cancelled, it's just n, isn't it? Minus e to the power same term, right? So it's negative, that's all, minus j pi into fs minus t, sorry, fs into t minus n. So that is fs times t minus n whole divided by, here I will take the j2 pi outside. When the j2 pi goes out in the denominator, what do you get? When the j2 pi goes out, j2 pi, there is just t minus n by fs, isn't it? N by fs. Okay, so this is the term. Now you can see that there is a sine function present, right? So let's try to write the sine function now. So that is equal to, so e to the j theta minus e to the power minus j theta divided by 2j, correct? So that can be directly replaced as a sine function, isn't it? So let's try to write that. So this is equal to 1 divided by fs summation n equal to minus infinity to plus infinity. This is g of n divided by fs, right? E to the j theta by e to the minus j theta by 2j is a sine function, right? So this is, I can write sine of pi fs t minus n whole divided by, the j2 is not there now, simply pi into t minus n by fs. So this actually I can try to simplify further. So I can take a common denominator and I can try to modify this. Okay, so that means this is equal to, there is a 1 by fs here, summation n equal to minus infinity to plus infinity, g of n by fs into sine pi fs, sorry, there's a bracket, I'll rewrite. Okay, so there is a pi times fst minus n all divided by, I'll try to multiply and divide by the fs over here. So what happens? This is pi fst minus n whole divided by fs. So this fs cancels with this fs. So I can see that sine theta by theta, which is a sinc function, correct? Sine of pi theta by pi theta means it's a sinc function. So I can directly replace that. So this is equal to, right, summation n equal to minus infinity to plus infinity. So the function is still the sampled function which exists inside the bracket, right? That is g of n by fs into, see the sinc function, correct? This is sinc of fs times t minus n. Okay, right? So I got this. I'll hold on to this equation for some time. Let me try to look at the equation number we have used. 1, 2, and now this should be 3. Okay, 3 is used. So let's go to the equation number 4. So let me try to see what was there on the left hand side. Left hand side is still the same summation we used earlier. Okay. So what we do now, we already know something about the GI of t. Okay, let's check the GI of t now. So GI of t is already present in one of our previous equations. Yeah. Okay, I think I need to call this as also one equation. Let me call that as equation number A. Okay, GI of t. Right, so you can see that GI of t is equal to n is minus infinity to infinity, g of n by fs into this, correct? So that means you compare this equation A with the equation number 4. So equation number 4 on the left hand side I have something, correct? So the left hand side I'm going to equate now. So what is the left hand side? This should be equal to the gi of t, because gi of t is right hand side and this right hand side of the equation 4, they are same. Okay, so I can write now. So this is what is my conclusion. So equation number 4 is equal to equation number A, right? So that means equation number 4 and equation number A are same, means that their right hand side I should be able to equate. So on one, in the first equation I have gi of t as the left hand side, whereas in this case the left hand side is right. Anyway, it's not visible here, I'll write. Okay, so that is summation m is equal to minus infinity to plus infinity integration minus of fs by 2 to plus fs by 2. This is capital G of f minus m times fs, f minus m times fs into e to the power j 2 pi ft df. So I'll just show you this same equation. Just compare this, whatever we have here, right? Same thing I have in the left hand side of equation number 4. So just check this term. This is the left hand side of equation number 4. All right. So both are same. I'm simply equating this with the equation number A. Is it okay? All right. So in the next step, I got this. Now we know that I have to have, I cannot keep the f minus mfs whenever I try to do the integration or the differentiation. So because of that reason, I need to make sure that I will try to write a substitution over here. Okay, so the substitution will be, you are going to put f dash is equal to f minus uh, I think I have f minus, yeah. So f dash is equal to f minus m times f, m times fs. So this implies there is a df over there. So what happens to the df? Df will be same as the df dash. So I can try to replace every df by df dash. Okay, so this implies the df dash will be equal to df. I can replace every df by df dash. So that implies, try to make this substitution in the integration. This means the gi of t is equal to summation m equal to minus infinity to plus infinity. Right now you see the limits are for f dash. F dash is equal to m minus 1 by 2 f to m plus 1 by 2 f. So I have g of f minus m, mfs is f dash, okay, into e to the power j 2 pi. You see there is a f, right? What is f now? F dash minus m, f dash minus m times fs. Okay, so how did you get that? So find f here, right? So if you want to find f, this is f dash uh, minus m times fs, correct? So we substitute in that way. Okay, now, so that means try to substitute this value into, there is a time term, so multiply this by t. Okay, so this is this into t df dash. Okay, so moving further, I can try to take the see the integration is with respect to f dash. So any term which has no f dash, I can take it out. So because of that, now I am going to write this is equal to summation m is equal to minus infinity to plus infinity, right? E to the power. So you see this mfs into j2 pi, that term has no f dash in it, correct? So I can move it outside the integration, right? That's what mathematics says. If you don't have a term containing the variable of integration, you can take it out, you can move it out, right? So let's try to do that. So when I move out, this is e to the power minus j 2 pi, there is m, there is fs into t. This is what I'm going to move out. Remaining terms I'll keep it as it is. So that means this is m minus 1 by 2 times fs to upper limit m plus 1 by 2 times fs, okay, into g of f dash into e to the power j 2 pi f dash t df dash. Okay, fine. Now anyway, I know that it is a dummy variable, right? F dash is a dummy variable. Every f dash you have, you can simply replace by f, right? So I can try to do now. So this implies f dash can be replaced by f. So that's a, it's called as a dummy variable. Can be replaced by f, which is nothing but it's a dummy variable. So still the same equation is retained, that is gi of t is equal to summation m is equal to minus infinity to plus infinity. This is e to the power minus j 2 pi m times fs into t integration. So you see now I'm going to replace f now. So this is f is equal to m minus half, right, times fs to m plus half times fs. So this is, you see, g of f, not f dash, into e to the power j 2 pi ft df. Okay, so I got a gi of t. Now let me call this as equation number, what is the number, about 5. So this is equation number 5. Now what I do, I got an equation for gi of t, and I already have an equation for g of t. Where is the equation for g of t? Let me just find out. Yeah, so you see equation number 2 is, right? Can you see equation number 2 is the g of t on the left hand side. So equation number 2 and equation number 5, I am going to put in equation number 1. That's the epsilon equation. Okay, so put 2 and 5 in 1. Put equation number 2 and equation number 5 in 1. So what is equation number 1? On the left hand side, I have the error, that is epsilon. So if you remember, epsilon is equal to magnitude of g of t minus gi of t. So epsilon should be equal to, I am taking a magnitude, I'll write the equation we found in equation number 2 for g of t, right? So that is summation m is equal to minus infinity to plus infinity. There is integration, right? This is m minus half fs to m plus half times fs. This is g of f, g of f into e to the power j 2 pi ft df. This is the equation for uh, the g of t. Subtract from this the equation number 5. So that is equal to summation m is equal to minus infinity to plus infinity. See, this is the extra term I am going to get. Before the integration, I have e to the power minus j 2 pi m 2 pi m fs into t. See, this is the extra term which I don't have in the first term. Then you have the same integration, that is m minus half times fs to upper limit being m plus half times the fs g of f into e to the power j 2 pi ft df. Okay, whatever is common we can try to take it out, right? That means I can try to write this as, I'll try to write like this, just verify whether it is right. Okay, so I'll write a summation outside. Summation m is equal to minus infinity to plus infinity. I'll try to take 1 here because everything is there in the first part. And in the second part, I have e to the power minus j 2 pi f, what is that? 2 pi fs into m into t, right? This is what it remains when I take out the integration outside. So that is on the lower side I have m minus half fs to upper limit m plus half fs times, see, this is what goes out. It's common everywhere, so we are taking it out, e to the power uh, sorry, it's g of f into e to the power j 2 pi ft df, its magnitude. All right. Now, see, there is what is called as a triangular inequality, right? The triangle inequality says, I'll call this is equation number 6. Left hand side is still epsilon, right? So using the triangular equality, we studied this in mathematics. It says that when we study triangular inequality, it says that magnitude of the sum is always lesser than the sum of the magnitudes. Okay, have you come across this somewhere? I'll try to write an equation so that if you can relate, right, you can try to do this. So that means magnitude of the sum, okay, magnitude of sum of maybe x plus y is always lesser than or equal to sum of the magnitude, sum of the magnitude x plus y. This is what is the uh, triangular inequality. Okay, so sum of the magnitude is less than or equal to magnitude of the sums, right? So it's like that. Sorry, I told reverse. First thing is magnitude of sum. So this is the, I can write the magnitude of sums is less than or equal to, this is sum of magnitudes. So there is a summation outside, right? So that is a sum of, I have some magnitudes being taken, right? So this is what is equation number, okay, let's call this is 7. So using this 7 in 6, I can write left hand side is actually lesser, correct? So epsilon should be lesser than or equal to, I'll try to write in this way. So this implies epsilon should be lesser than or equal to, right? Now I try to move the sum outside, summation outside, you see, because it's magnitude of sum, correct? So I have a magnitude outside and inside the sum. So this is actually lesser than, if I try to move the summation outside this, magnitude, it becomes it is lesser than, right? So what I do, I'll try to take the summation outside. So summation, this is m is equal to minus infinity to plus infinity. Then you take the magnitude. Okay. So we'll try to take a magnitude now. So summation has been moved out. Then I'll try to write the remaining terms as they are. So that is 1 minus e to the power minus j 2 pi times m into fs into t. This bracket closes. Then you integrate from m minus half times fs to m plus half times fs g of f into e to the power j 2 pi ft df, its magnitude. Okay, so this is actual equation to calculate the error due to aliasing, right? So anyway, g of f e to the power j 2 pi ft will give you a function. Multiply that by 1 minus e to the power minus j 2 pi fs m into fs into t. Take the summation all the over from m equal to minus infinity to this. So this is the general equation. We'll try to cut short this into a smaller equation now by doing some assumptions, right? So so we know that for the central term, because in the spectrum, I want to look at only m equal to 0. Okay, but if m equal to 0, what happens to this term? 1 minus e to the power minus j 2 pi, what is this? E to the power j 2 pi m fs into t. For m equal to 0, what happens to this? Fst, because m is 0, e to the power 0 is 1, so 1 minus 1, that becomes equal to 0. That's my first point. Right, and also I'll try to make a magnitude now. So magnitude of 1 minus e to the power minus j 2 pi m fs into t, right? If you try to take a magnitude, this is always lesser than or equal to 2. Maximum value is that 2, because e to the power negative number is always lesser than 1, right? E to the power minus whatever, you right, is less than 1. So maximum value is 1 when it is 0. So e to the 0 is 1. So 1 minus, right? Minus 1 can be plus 1 plus 1. So that is equal to 2. Is it okay? In addition to that, right, we can try to write another notation. Everything is taken from maths. So this is equation number 9, this is number 10, and also I'll write another one, that is magnitude of integral, that is m minus half fs to, this is m plus half fs into g of f e to the power minus j 2 pi f t df. Its magnitude can always less than or equal to, because since there is a e to the power multiplied getting multiplied with g of f, its value is always lesser than this value, that is m minus half fs to m plus half fs. Okay, simply take a magnitude of g of f, right, df. So this is equation number 11. So I use equation number 9, 10 and 11 in 8 to get a simplified version. So I'll try to make sure that. So this is 8, comma 9, comma 10. Is it 8, 9, 10? Sorry, 9, 10, 11. My mistake. Okay, try to put 9, 10 and 11. 9, 10 and 11 in 8. So you see it simplifies to now. I'll try to write it here. So that is epsilon should be lesser than or equal to the magnitude, the 1 minus e to the power j, right? Highest magnitude is 2. So it should be lesser than 2 times integral. So I'll write magnitude of f right? It should be, right? I cannot write 0, right? Because m equal to 0 is not valid. It should be greater than 0. When you put m equal to 0, what happens to the limit now? This is m minus half fs, right? I cannot put m equal to 0. You should put at least m equal to 1. So that means f should be greater than fs by 2, correct? More than that, it cannot be 0. When it is 0, it is fs by 2. You cannot take fs by 2. So that means it has to be more than fs by 2. So magnitude of f more than, right? It is fs by 2. Then you write magnitude of g of f df. So this is the final equation which you are going to use to calculate what will be the aliasing, right? If you know what is the g of f, right, and what is the fs, you can calculate the error due to the aliasing for a given fs. So you see, you change fs, you get different amount of errors. So ultimately the fundamental concept still remains same, right? Depending upon the fs value, you keep getting the different values of error. This is valid for the sampling frequency lesser than twice the maximum frequency content of the signal. Okay, if it is more than that, this error becomes 0. I know that there is no aliasing, so no error, correct? Okay, but when the sampling applied by us is not following the Nyquist rate, you can use this equation to calculate the amount of error. Okay, so this is the whole concept about effect of aliasing. When aliasing is there, how much error is there, we can calculate in this particular case.